Hello, everyone. Welcome at the TCS seminar at the Ljubljana University. Today, our speaker is Sergio Cabello from the University of Ljubljana. Well, Sergio is in Ljubljana since I remember, so it must be at least 15 years, and I actually don't know the story. And for what I read is that you finished your PhD in Utrecht. And I assume that you finished your studies in Spain, in Barcelona, perhaps. But what I know is that Sergio is well recognized for his contributions in computational geometry, also in computational topology, in general in graph algorithms. And it's great that you accepted our invitation and you joined us today. And please take us from here.
Thank you very much. So I'm gonna share the slides. Having here, so we just make a share of the whole screen, which is gonna be the easiest, I guess. Okay, so let me arrange this to find myself. So I will be talking about packing d-dimensional balls into d+1 dimensional containers. As Piotr was mentioning, I'm in Ljubljana. Actually, I think in February will be 20 years. It has been for quite some time. And Piotr was mentioning I studied in Barcelona. Actually, that's true. And actually, I'm right now in Barcelona. I'm visiting Barcelona right now. So this is joint work with Helmut Alt, Otfried Cheong, Jimon Park, and Nadia Seifert. And here it's available in archive already. So you might be a little bit scared by the date because it's 21, but actually we just uploaded a new version where you can see the results that I'm going to present. So the previous version was without me, and now I got involved into this research. So let me start describing what's the problem we're going to be looking at. So we're going to be working in a fixed Euclidean space. So we fix dimension d+1. And we're going to be talking about d-dimensional balls, unit balls actually, in space d+1. So we had to fix d to be the dimension of the ball or d to be the dimension of the ambient space. And we went with d being the dimension of the ball, and then we work in one space higher. And today, all hyperdisks are going to be unit hyperdisks. That means unit radius. And later at some point, we will need radius 1/2, but that will be a very precise point. And I emphasize this because sometimes I will forget to tell unit. And also sometimes instead of telling a hyperdisk, I will be talking about a disk, and that's because I forget the hyper. So the standard setting we are thinking of, for example, here is unit 2-dimensional disks in 3-dimensional space. And then when you think in this way, quite often you, you forget to put the hyper. Okay. And what are the kind of problems we're going to be looking at? So the input or the data that we have is n unit hyperdisks in dimension d+1. You could think they are described by the normal vector. And you could center them at the origin because we're going to be making translations. So you can just put all of them at the origin. And then the task is to pack the hyperdisks using only translations into a d+1 dimensional container and minimize the volume of the container. Okay, so in this example, we would have a bunch of disks. As I was telling before, because we're going to make translations, we could just place them at the origin, centered at the origin, but then it's harder to see anything. Then we want to make translations and we pack them into this axis-aligned cube. And the task is to minimize the volume of the container. Okay. So, of course, this problem, once you allow rotations, it becomes trivial because hyperdisks have no volume. So you could rotate all of them to be the same, and then you would have arbitrarily small. But as you can imagine, once you are only allowing translations, life becomes more challenging and therefore interesting, I would say. So what does it mean, pack? or packing. So we want that the relative interiors are pairwise disjoint. So somehow when you talk about packing, you allow that the boundary of the objects are touching. Here, because they have no volume, so what you have to do is the correct way to look at it is to tell that the relative interiors are disjoint. So this can be touching, but only on the boundary of one of them. The boundary of one of them together with the interior of the other, that's also fine. I was telling containers, so we will talk about 3 types of containers, but actually they are closely related, as we shall see. So the first one, we will talk quite a bit about axis parallel box container. So if here we have this axis system, so it would be a rectangle like this in 2D, axis parallel box in 3D, and so on. We will also talk about arbitrarily oriented box. So the box can take any orientation, and then also about convex bodies. With the container, you want that is a convex body. In all cases, we try to minimize the volume. And as I was mentioning before, rotations are not allowed. And by the way, I didn't mention it explicitly, but just jump in with any questions at any moment, if you wish. Actually, there are 2 types of problems. So besides different types of containers, there are 2 different flavors of problems we could look at, and we will talk a little bit about both. So one of them is the algorithmic problem. So the input is a collection of n-unit hyperdisks in dimension d+1, and we want to find the minimum volume container where you can pack the hyperdisks under translations. Usually you also want explicitly the packing, not just I can pack them here, but how do you pack them? And then there is also the mathematical question, which is which family of n hyperdisks asks for the largest volume, requires the largest volume, and which one is this volume? This would be find a tight bound, let's call it F, depending on the number of disks n and the dimension d of the hyperdisks, so that each set of n-unit hyperdisks can be packed with translations into a container of this volume, F and D. And you want tight bounds for this. Okay, there are both things, the algorithmic, and somehow one could think the worst case over all possible inputs also. Okay, so what kind of results do we get? So the algorithmic problem, so given n-unit hyperdisks, find for that concrete data best container. So we get constant factor approximation for each fixed dimension D. And here, well, you can see the constant. It's not really terrible. It's D to the 3D or 7D or something like this. It depends on the container, of course. But the point here is that it's a constant factor approximation. Okay. As I will mention at the end, actually, we do not know whether the problem is NP-hard or not. It would be surprising that it would not be NP-hard. But in particular, we don't know whether a pitas could exist, for example. But it's a constant factor approximation. We didn't work really hard to improve the constants. So we looked more into getting numbers that are easier to parse, and not so much into trying to get the really best constant that one can argue with the ideas that we have. And for the mathematical problem, which I find very interesting, the volume that, this function f and d is theta of n to the d-1 divided by d. So to get a feeling for this, so it means that for dimension 1, so this is packing unit segments in 2 dimensions, you can always do it with bounded volume, so with bounded area. It's independent of n. But for packing 2-dimensional disks in 3-dimensional space, you need a volume. In the worst case, there are configurations where you need this much volume, square root of n, and you can always do it with the square root of n, asymptotically. And here, of course, there is an interesting feature, which is for unit segments packing in the plane, it's constant area, while in two-dimensional disk in 3D, you need increasing volume as n increases. Okay, so I will actually explain a little bit more about this in a second. So the rest of the talk is on how I'm going to be explaining some ideas. So this is the summary of the results. I will not go so much into the details. I will explain the main ideas, how I want to achieve this. As a warning, I'm aware that the seminar is TCS. Actually, here there will be quite a bit of geometry, which is elementary. So I think that you will follow the geometry without any problem. The algorithms are actually quite simple. So once you understand the geometric properties of what you're analyzing and studying, the algorithms will be Hamiltonian path problem or something like this. But otherwise, it's not very advanced algorithmic. But the geometry is simple, nice, and I would dare to say cute. So as a warming up, let me talk about the problem of packing unit segments in 2D. So you want to minimize the area of the container. So here on the left, we would have unit segments centered at the origin, collection of them. And then one way to pack them is just to translate them so that they have a common endpoint. Okay, and this will give always constant area. Because actually what you're getting is a container. I mean, here a container, I'm thinking of axis parallel box as a container. So you can get a container of area 2. I mean, this is a rectangle of height 1 by width 2. And you can place all unit segments here. Actually, by all, I mean the infinite family of unit segments. You can pack them here. Okay. If you would be looking at a convex container, I would dare to expect that this semicircle, this semi-disk, is the solution. But I have to be, I'm not sure actually, because, in set theory, weird things happen sometimes. And I'm not a specialist in measure theory myself. So, you can pack as many segments in a rectangle of, parallel segments in a rectangle of width 1 or width 3. So perhaps something weird could happen here, but I would not expect so. If you restrict yourself to axis parallel rectangles, this is actually not the best. So this one has area 2, this axis parallel rectangle where we can pack all unit segments. And there is a way to do it a little bit better. And I'm explaining this as a curiosity actually, so we move from this semicircle, we can cut it into this way. So here we can also pack all unit segments. The ones of positive slope are here. The ones of negative slope are here. Then you can take a small piece here and place it here above because there is a space. And now here the distance is non-zero. So you can reduce the rectangle a little bit. Okay, you can reduce the width of the rectangle a little bit. So this would be 2 minus epsilon width for some epsilon, and the height keeps being 1. So this shows that 2 is not the correct answer. And we didn't explore this problem, but this problem sounds quite reasonable to me also. Like, what's the best container? What is the best rectangle axis parallel where you can pack all unit segments? So I think this is a nice, cute problem.
You have a lower bound.
So definitely it has to be a constant. Because if you pack horizontal and vertical, you will need something. But I'm a little bit scared of this measure theory thing. I'm not a specialist. So as I was telling before, I would expect that this is the best convex container. So that would be also a lower bound in itself, but no, we didn't look into this. So we were more interested into higher dimensions. So this was just like warming up. So I look into this case because my co-authors wrote that area 2 is not the best. And then you start thinking why it's not the best and what comes to this. Such container is not possible in 3D. That's what I was telling before, because when you want to pack n-unit disks in 3D, two-dimensional disks in 3D, you will need a non-constant volume. Okay. Closest related problem. Actually, there is not much work on this. Actually, I'm not aware of any real related previous work. But what seems to be the closest is the so-called potato sack theorem, which does the following. I mean, this is a well-known theorem. So if you have a sequence of convex bodies in R to the D, and you have a bound on the diameter on all of them, and you have a bound B on the sum of the volumes, all of them together, then you can pack them into a cube whose side or volume or diagonal, it only depends on A, B, and the dimension. In the packing, in this case, is using rigid motions. So this what this was telling is assuming that potatoes have bounded diameter, so you can always pack a certain volume of potatoes into a sack with a certain volume. This problem was, well, problem 10.1 by Auerbach, Banach, Mazur, Ulam in the so-called Scottish book.
But here again, it's the translations only, right? Or
so you need rigid motions here.
but these convex bodies, you can just translate, no rotations, right?
In our setting, you can only translate. In
Okay.
this problem, you're allowed to make rotations.
Oh, okay, yeah, okay.
So rigid. What are rigid motions?
So any motion that does not deform the object. So rotations plus translations. That would be a rigid motion.
And here in this problem, these objects are in the D space as well as the ambient space. Yeah.
Yes.
That's a difference. Yeah. Okay.
Yeah. So sometimes they are also called isometries, rigid motions. Thank you for the questions. So this is a problem. I don't know whether posed. I mean, so it was posed as a theorem without a proof in the so-called Scottish book, which do you Polish people know in the Scottish book? Okay, so outside Poland doesn't seem to be so well known. Like I gave this seminar one other time and nobody had heard about it. But there was no proof there. And Kosinski proved it, published a proof in 1957. And to get a feeling of this research area, so one can look at the nice survey by Gabor Fejestoth that was just published last year, which is about packing and covering for sequence of convex bodies. Because of course you could consider this problem also when you put extra constraints on the convex bodies. Like if the convex bodies are cubes, what happens? Or if the convex bodies are ellipsoids, what happens? And so on. In particular, the online problem has been also studied. Okay. So that's somehow the introduction. I mean, so I explained the problems we're going to be looking at, the closest related work. So now we'll move on to the ideas. How does one prove our results? So first we will consider a stabbing problem, which is closely related. And in particular, we will study the connection between the stabbing and the packing problem or hyperdisks. So this stabbing problem is actually gives the solution for the packing or an approximate solution for the packing problem whenever the hyperdisks are similar. That hyperdisks are similar, it means that the normal vectors are similar. Okay, so the angle between the normal vectors is sort of small. And then the idea is to cluster the hyperdisks depending, to groups that they have similar normals and solve each dimension separately and do a little bit of cutting and pasting. As I already said before, there will be some geometry. The algorithms will be easy actually. Okay, so what's the stabbing problem? We're going to be looking at quite a bit now. So we are in dimension d+1, so the ambient space is d+1. We have hyperdisks of dimension d. They are unit hyperdisks. And then we have a line L. And then the task is to pack the hyperdisks using translations. But now we want that all of them have the center placed on the line L. So it's like making a skewer or stabbing the hyperdisks through the center. Okay, and we look into packings that you get in this way. You could look at two different criteria when you look at this optimization problem. So one of them is that you minimize the length from the first center to the last center of the skewer. The other is that you project the hyperdisks onto the line, and then you look at the distance between the first point in the projection and the last point in the projection. And what happens is these two values are closely related. We will see later. But also, what happens is that the center-to-center distance is much easier to analyze. So that's the reason why we talk about this one, the center-to-center distance, while actually the object we are really interested in is the first one, the length of the projection. But they are closely related, and the second one has nicer properties. Okay. So the line L is fixed, is part of the input, you're not allowed to change it. Okay. So what do you gain by looking at this? So first of all, it's a discretization. So once you have the order of the hyperdisks decided, how they're going to be pierced by the line, that discretizes the problem. I mean, so when you add the next disk, I mean, the next hyperdisk, you should be careful to don't be overlapping with the previous ones. You could be adding one by one. Actually, the key property that we will see now is that if you want to check if such a piercing, such a stabbing is a packing, you only need to look at consecutive hyperdisks. So it cannot happen that the first hyperdisk touches the third unless the second is touching the first or the third. Okay. So this actually tells you, I mean, it's not just a discretization only, but it's a linearity. I mean, it turns the problem into completely linear when you only need to check adjacent pairs. And that's actually not obvious that you only need to care about consecutive. And the reason for this is actually that there is a metric going on behind. And let me define this metric. So we have the line L like before, and then we consider two unit hyperdisks. I mean, this is going to be a metric only because we have unit hyperdisks. If you have hyperdisks of different sizes, everything breaks apart on this. So we have two unit hyperdisks, and then we define the distance with respect to L of the two hyperdisks to be the distance between the centers when we pierce D1 and D2, and D1 and D2 are touching. I mean, so it's a packing of a smallest volume. So in the case of unit segments, we will be having here a segment, and then we will be looking at the distance between the centers, the Euclidean distance. And the key property is that this defines a metric. And actually the triangular inequality property is the one that is telling you that, you know, the distance from this to this and from D2 to the third one has to be larger or equal than the distance between D1 and D3. And therefore, there is no interaction between D1 and D3 once consecutive ones are being packed. And that's actually the main thing that one has to argue. So to argue this, that you have the triangular inequality, which is the challenging part. I mean, symmetry comes just by exchanging the order of the hyperdisks. or rotating everything by 180 degrees. And the distance is non-negative. It's trivial because it's always a length. And these are the distance is 0 if and only if you have the same hyperdisk. It just means you have to define the two hyperdisks are the same when they have the same normal vectors, so one reverse of the other. But the challenging part here is the triangular inequality. And basically the main idea to show this is, let's assume that it is not true that it holds the triangular inequality. So the distance from D1 to D2 plus the distance from D2 to D3 is strictly smaller than the distance from D1 to D3. Then you put a configuration of the first one and the third hyperdisks where they are touching. So they are achieving this distance. So they are touching at some point P. And then you restrict attention to the two-dimensional plane that is defined by the line L and the touching point P. And then your task is to argue that, well, okay, so the intersection of D1 with this plane is a unit length segment. The intersection of D3 with this plane is a unit length segment. And the intersection of D2 with this plane is another unit length segment that is not drawn. And what you have to argue is that you cannot draw it here unless you introduce some intersections. That's the task. And then you massage the geometry a little bit. I mean, you argue that this region here becomes larger when the tangent, the point where they are touching, they are actually boundary points of both disks, and argue a little bit of geometry. But it's simple in the sense that it's just two-dimensional geometry from this point on, independently of the ambient space. Okay. So to me, this is one of the key insights of the whole discussion. I mean, one thing is to consider the stabbing problem, and the other thing is to realize that there is a metric underlying here. Okay. This is just a nutshell of the ideas that are being used. So this tells that the stabbing problem, you can get a order 1 approximation, a constant factor approximation. And the idea now is simple. So you have to decide in which order you stab them. That's the order is a Hamiltonian path problem. I mean, it's a bijection between Hamiltonian path in the graph that has segments or has the hyperdisks as has the hyperdisk as vertices, and the distance between two vertices, the length of the edge connecting them is just this distance that we defined. Hamiltonian path tells you in which order you are piercing them. And if you compute an approximation for the Hamiltonian path, you're just getting an approximation for the center-to-center distance, because that's what we were measuring. You're adding this distance here, plus this distance here, plus this distance here, and so on. So that gives a 3/2 approximation, because Hamiltonian path in any metric can be approximated 3/2. And if you look at the length of the projection, you just have to put a +1 in the approximation factor. Because here, whatever sticks out is going to be a segment, and any solution, I mean, a segment is going to be a length there in the projection, and any solution is going to have at least that 1/2 of opt. And here is the same. The last one that sticks out the most is going to give 1/2 of the opt. So this is what I was telling by the algorithms are simple. What you have to do is to figure out the geometry. Okay. There are some bounds that one can argue on this metric, and they come useful when you want to look into approximations. And the bounds are using a bit of geometry. So if you have the line L, you have two hyperdisks. And the hyperdisks have normals N1 and N2. Then you look at the angle that the two normals are making. Okay. So the sinus of that angle is a lower bound on this distance with respect to L. And then if these two disks the normals don't make a large angle with the line L, so they are bounded, then you get this upper bound. So it's the same values we were having here, divided by the cosinus of the normal, the angle of the normal with the line. So what is this telling is when the normals to the hyperdisks are sort of close to the line that you use to pierce them, the sinus between the normals is a constant factor approximation. So you can just use the sinus between the hyperdisks, use that for approximation. This is correct when the bound, I mean, when the angles that the hyperdisks, I mean, this is like L is piercing the hyperdisks quite orthogonally, let's say. Not at 90 degrees, but quite nicely. In particular, computing this kind of weights is non-trivial numerically, but computing the sinus between two angles is quite easy. I mean, the sinus between two normals, or the sinus. So if you're willing to get here a worse constant, you might just use the sinus, assuming that all hyperdisks are sort of similar. Okay. So I can explain a little bit.
Can you go back for a moment? So this works well if this angle between a norm, each norm and the L is
bounded away from
90 degrees, yeah?
Yes.
Okay, and so it's independent. How do they behave with each other? Or,
Yes.
no, there's the sinus of the Xi, and Xi is I see. Okay, I understand. Sorry.
Sure. Thanks. So I want to explain a little bit of the ideas how one comes to this kind of bounds, but actually the only thing why I'm going to explain the idea is because there is a configuration that is a little bit more weird, and if you are not warned, you might miss that such configurations exist. Okay, it's not just to so we have this drawing here. So you have the two hyperdisks, D1 and D2, and then consider to place them such that the distance between the centers defines this distance, and let P be the touching point. Now each hyperdisk is containing one hyperplane. Let's call it HI, the one that contains the I. And then you look at the intersection of the two hyperplanes, H1 and H2. So this is a d-1 dimensional flat. And the touching point has to be in this d-1 dimensional flat, because that's the only place where the two hyperdisks can touch. So usually you have this kind of configuration where you have in mind. I mean, there is one hyperdisk that is contained in this hyperplane. It goes farther from this half hyperplane. And then you have the other one touching somewhere in the center. I mean, somewhere in the inside. But there is this kind of configuration also, which is drawn in 3D. So what you have is the following. So this is a different drawing. So let's say that you put them, the two disks, two-dimensional disks, you put them in one plane. In this way, you choose a point where the boundaries intersect P, and then you take a line that passes through P, like this. And now you rotate one of the disks a little bit around G. So the two disks are going to be touching only at the point P after the rotation. But it's, so they are both touching in the boundary of both. And the difference is here you have one of the hyperdisks is contained in one half hyperplane, but here that is not happening. So the hyperplanes that contain the disks, each one of them crosses the part of G. Okay, so this is the kind of what happens when you make the rotation. Okay. This, I mean, now you would be stabbing still these disks through the center. So this might look a very weird thing, but something similar can happen also when they are very nearby. Okay. And this is a configuration that, what should I tell? It's easy to miss. Okay. And when you argue this inequality, so you have to be careful to keep this one in mind. That's everything I would. So here what you have is that you have this d-1 dimensional flat G, then you have an orthogonal one that has 2 dimensions, and then you can use orthogonality to argue things about the distances. That's basically everything I would tell as a warning when you see this kind of inequalities, what goes behind. In particular, the kind of things you have to use is that this kind of flat is intersecting both hyperdisks, and the intersection is actually a ball of 1 dimension lower. So here it is a segment because we're in dimension 2 in the equals 2, but it will be dimension d-1. Okay. So let me now talk a little bit about the relation between the stabbing and the packing problem. Okay, so I was telling, we started looking at this packing problem. And then I said, oh, let's discuss stabbing. So of course it's because there is a relation between them. So we fix an angle, phi sub 0, phi null, defined like this, arc cosinus of 1 divided by this. So what is this number is, so any vector makes this angle with at least one of the axes. Okay, so later we will be clustering the hyperdisks depending on the normal, which axis is the closest. And this is the kind of threshold that you need. And then we consider a configuration where all hyperdisks have at most this angle. I mean, the normal of the hyperdisks have at most this angle with one axis. So we choose the last axis. Okay, so in 3D, this would mean like we look at the vertical axis, I mean the last one, and then we are looking at disks whose normals are roughly similar to that axis, and actually not that similar. So it's just a constant angle what we are having. I mean, it's not really like very similar, the directions, but bounded away from pi halves. And let's call opt the volume of the optimal axis aligned box where we can pack this family of hyperdisks. Okay, so the claim is that there exists a stabbing of the disks by this last axis, by the vertical axis, that has length proportional to the optimal volume. And in particular, also the volume of this stabbing. So when you stab all of them, you could put just a long box where you enclose everybody. So in all the other dimensions, they're going to have length 2 at most. So the length of the stabbing is basically telling you the volume. Okay. So that will be also order optimum. And this tells, like in this particular case, the stabbing is giving a constant factor approximation. Okay, so when all the hyperdisks have, well, a small angle with the last axis, then the stabbing with by that axis is actually a constant factor approximation. So let me mention the key ideas for this. So here we are having the last dimension. So you should think in 3D, this is the third dimension. And then here we have the rectangle defined by the other dimensions. So M1 times M2 times M3 times MD. The product of, I mean, these are the lengths of these edges. Okay, so this is an optimal solution, a box where we can pack all these hyperdisks. So they have this volume, M1 times M2 times MD+1. You should multiply it by this. And what we do is we put a bunch of vertical segments that they will touch all the hyperdisks. So we make these many segments. So this is going to be like a grid, a regular grid with these many segments, each one of them of the same length, of this length. Okay. And we have to select this. And now the point is, I mean, these hyperdisks, they are, I mean, if we are thinking of this vertical direction, so these hyperdisks are sort of moved a little bit like this. So the projection onto the first d dimensions is going to be a fat object. I mean, because you cannot have a very tilted hyperdisk because they are like this. When you project them down, they're going to be a fat object. So this means that you have a grid, a regular grid at constant distance, where this constant depends a little bit on the dimension because it depends on this angle also. But you have some constant that depends on the dimension, such that these segments are piercing all the hyperdisks in the packing. So that's the reason that we have this many segments or this many grid points. So it depends only on the length of this axis, because the distance here is constant, the distance here is constant, and so on. If you choose this grid with a smaller constant, you can guarantee that the point where a hyperdisk is pierced is actually near the center of the hyperdisk. So it's a distance, let's say at least 1/2. This is just decreasing the constant of how spaced these grid points are. So now, each hyperdisk is pierced by one of these segments, and it's actually as close to the center, at distance almost 1/2. So what this means is that one such hyperdisk of unit radius, you can replace it by one hyperdisk of radius 1/2 that is contained in the original one and is centered at the point where it was piercing. Okay. And now what you get is a collection of hyperdisks of a smaller radius, radius 1/2, but all of them are pierced by these segments through the center. So we have gone from piercing outside the center a unit disk to piercing a scaled down copy of the hyperdisk through the center. Okay, now what you can do is you take these segments and you place them, all of them like this, together with the hyperdisks of radius 1/2 that they are piercing. So this hyperdisk that was here would be somewhere here. So it's like taking a small piece of this rectangle or this box and putting them one after the other, making a longer skewer, all of them together. So what you get in this way is a stabbing of hyperdisks that are copies, scaled down copies of the original ones with radius 1/2. And now you just scale the whole image by 2 in all dimensions.
Okay, but how do you know that they don't overlap?
Okay, very good question.
That the glue.
Well, the hyperdisks that are pierced by this, they are contained in this thing, so they don't stick out of this box. And the hyperdisk is contained in the box together with this segment. What should I tell? So when you're taking this segment, so you're having some upper side of the segment and some lower side, and the rectangle, the hyperdisks are contained here inside. They don't allow to stick out or stick in because they can be packed in this thing. So when you do this, so you can think like there is a boundary here, and everybody who is stabbed by this is not crossing this part. Everybody who is stabbed by this is not crossing this part either, because you're concatenating the the lower and the upper boundary of this box also. So
Okay,
that makes separation between different ones.
makes sense. Yeah.
Yeah. Mhm. Thanks for the question. And now the length of all of this is, well, it's M1 times M2 times M3 times MD+1, because you're concatenating these many segments, and each one of them has this much length. So the whole concatenation has length order opt. And when you scale it by 2 in all dimension, you will just have an extra constant factor. So that's the way how one relates the packing to the stubbing. So this tells you whenever you have a packing with volume opt in a container that is axis aligned box, then you can get a stubbing that is order opt volume and order opt length. Okay. So this solves the case when all hyperdisks are sort of similar. I mean, they make a small angle with one axis. So when you have different, arbitrary unit hyperdisks, so what you do is you break them into groups depending on which axis they minimize the angle. So basically you would get some of them that are mostly horizontal, some of them that are mostly with respect to the y-axis, some of them that are respect to the z-axis, and so on. For each one of them, you compute the solution with respect to stubbing. Okay, so with one of these, you get the stubbing. And then what you get is actually just a collection of these boxes. And now you have to be a little bit careful because they could look like this. So you cannot just take a rectangle, a box for all of them. But what you can do is to chop each of them. So let's say this one, what you can do is to chop it at certain distance, making cubes. Now this cube can have the problem that was worrying Piotr probably before, which is things could stick out. But let's say that you take the cube and now here you have to enlarge them a little bit so that the hyperdisks are inside. So you divide the disks here according to which part of the segment is crossing them. And then you take a little bit larger hypercube to put them inside. And basically what you do is you get a packing like this. You get an extra factor because of course rounding here, if you chop them into things of length 1, the segment that is piercing them through the center, you cut those segments into pieces of length 1. And at the end, you could have one that extra. But that's basically the idea. So being a little bit more careful, you have to be more careful because there are two cases. So one of them is perhaps all the hyperdisks have very similar normals. So there is a unique of this. And then you are fine with that solution because stubbing is just good. That's what we argued before. When two of the directions are non-empty, then you know that the solution is going to have constant volume. So when all of them are very, very similar, very parallel, it could be actually that the volume is arbitrarily small. Okay. But in that case, stubbing is good. So you don't care much. And when you have two directions that contain, at least two directions that contain some disks, then you just know that the optimal volume is going to have at least a constant volume because in each dimension you have a non-trivial thing going on. And then you can use this trick. Okay. That's basically the idea. So what happens? So this was about axis aligned boxes. So you need to fix some axis and break things. So what happens when you look into boxes in arbitrary directions? So you don't have any fixed direction, you're allowed to choose it. So what can happen in such a case is that you have to be careful because the volume could
Can I ask another question?
Yeah, sure.
Okay, so you reduce the kind of packing into stubbing in case for this axial-lined boxes, yes. But you did mention that there is some bad configuration that you it was for the axis-aligned boxes that you have square root n.
Yes.
Okay, is it something trivial that I should see immediately, or it's
that will come later.
oh, okay, sir. All right.
So the worst case, this is about approximation. But actually, so I can just, well, I will come back later to that.
Sure, okay.
Worst case. So this somehow is like approximation. Thanks. So when you have boxes in arbitrary directions, I mean, you're allowed to choose the direction of the box, the orientation. So what happens is the following. So for example, even for unit segments in 2D, I mean, if you have a diagonal segment, so of course the arbitrary direction could be arbitrarily a small volume. Because I mean, if all the segments are just like similar 45 degrees, the volume of the box could be arbitrarily small. But if you want a box that is axis aligned, it will have non-trivial volume always. So what this indicates is, well, you should, I mean, what you can do is you choose one hyperdisk, and then you use the direction given by the normal of that hyperdisk. If all hyperdisks are very similar to that one, the stubbing will be giving you a good solution. There is this kind of thing here. Like if all hyperdisks have similar normals, stubbing by a normal that is given by one hyperdisk will give you a good solution. In particular, it's like choose a axis system where one normal of any disk is one of the axes, and then stub by that. And that gives you a good solution if all the hyperdisks are similar. What happens in the opposite case is that not all hyperdisks are similar, but in that case, you can argue that the box of the that the optimal box is going to have it's going to have at least constant length in each dimension. So whenever you have two hyperdisks that are not very similar, you can tell, well, the optimal box is going to have at least, I don't know, length 1/2 or 1/4 in each dimension. And in that case, what happens is that it doesn't matter which orientation you use, because all of them are a constant factor of each other. And that's basically the idea. I mean, you look at the best of two solutions. One of them is computing the optimal with respect to a fixed axis, and the other is computing the optimal by using a stubbing in some normal, and you take the best. And for convex containers, life is similar, because there are these theorems in convex geometry that tell that whenever you have a convex body in dimension D, there exists a small box that contains it, and the volume doesn't increase much. By much is this kind of constant. Okay, so every convex body in dimension D can be put inside a box of volume, well, the volume of the convex body, and then some constant that depends on the dimension. So basically approximating a convex container or approximating an arbitrarily oriented box is very much the same problem if you are only interested in constant factors. Okay. Now we look at the worst case bounds, which is actually what Piotr was mentioning. So the normals, you can just represent them by one point in the unit sphere. That's the same as a normal. And then what happens is the geodesic distance inside, I mean, between 2 points, the geodesic distance on the unit sphere, the sphere of radius 1, is actually the same as the sinus between the two normals. And it's, well, it's not really the sinus. Well, it's roughly the sinus when the angle is small. And that means that it's roughly also the distance when the two normals you're looking, they are close to the line you use for piercing. So this is some sort of intuition or introduction. So what you do is you construct this kind of instance. So you put a grid around the origin. The distance here is epsilon, which is defined to be some constant times 1 divided by n to the 1 over d. So here you have dimension d, and then you project it to the sphere of dimension d also. Make this lifting. And this is the collection of normals that you're having. And now when you have this connection with Hamiltonian path of TSP, so basically any TSP of this configuration of points is going to have this kind of length, at least. It's n divided by this. Because, it's TSP, minimum spanning tree, they are constant factor away. And the minimum spanning tree is easier to argue, so or even the TSP here is fine. So you need to make, well, it's not a TSP, it's a Hamiltonian path. You don't need to return. But you will have like n minus 1 edges, and each edge has this kind of length. And so what this shows is a configuration of points so that every minimum spanning tree is going to have this length. And then because of the stabbing property and the distance, that is also going to be a lower bound on what happens when you stab all these disks. And for the upper bound is roughly the same. So it's known that, let's say, if you choose points on the sphere, so any endpoints on the d-dimensional sphere, they always have a TSP of this kind of length. So I don't know whether you know this or not, but the standard way to do it is like you can put a grid, as we are doing here, and then you make a TSP of the grid, which you could consider like a Steiner points, and then every point you bring it close to the closest grid point. So, for example, so this is just an instance of if you have n points inside the unit square, which one is the length of the TSP in this case. And what you can do is you just take a square root of n by square root n grid inside the unit square. Then you make a minimum spanning tree of this. And then every point you can then put it closer to the grid point that is there. And this shows that you can always do it of length square root of n. And if you go to dimension higher, then that appears in the degree of the root. Okay, so this is how the worst case bounds are argued. So actually, this is a configuration. So once you see this, it seems sort of a good candidate, a natural candidate. It's a bunch of disks that are tangent to a unit sphere. That's the lower bound of how you get a worst case scenario. The question is, if I would give you just this collection of disks, tangent or the hyperdisk tangent to a unit sphere, how would you argue anything about it? And it seems like this metric is the correct tool to look into it. So this is about the content. So I wanted to talk about this packing hyperdisk by translations and minimize the volume. As I was telling, once you allow rotations, doesn't make sense, the problem. And that's one of the reasons why I like this problem quite a bit. And you're packing you're packing zero volume things. But because you only allow translations, that's what makes it interesting. And there's some constant factor approximations. And there are quite a bit of problems here. So one of them, as I was mentioning before, we don't know whether the problem is NP-hard or not. Packing unit segments in 2D, I do not know what would be. Stabbing unit segments in 2D seems like should be doable in polynomial time, I would expect. But and also we don't know whether these problems are in NP, and actually would not expect so, because quickly the coordinates of how things are touching should become a pain. there is this problem I mentioned of if you want to pack all unit segments in 2D with a box, we know the answer is not 2. It's not clear what would be a good candidate. We are not allowing rotations, but one could allow some subset of the rotations. Like, for example, you could be packing unit disks in 3D and allowing only rotations around the vertical axis. So only allowing rotations to go around, and then translations. Or any other subgroup, but well, subgroups of rigid motions, or they are not that easy. There is also the question of packing not hyperdisks, but smaller dimension volume balls. Like, for example, d-1 dimensional balls in R to the d+1. So, for example, packing unit segments in 3D is also a constant volume. The same, you can just make a half sphere. But packing two-dimensional disks in 4D, I have a hard time imagining how to approach the problem. And that would be, in general, packing k-dimensional balls in RD. So when k is smaller than d/2, than d halves, it seems that there should be quite a bit of space. But, well, at least myself, I have problems to imagine all these kind of things. That's quite difficult, I think. And one other question people usually ask is, what happens if you have disks of different sizes, hyperdisks of different sizes? So if the ratio is not very large between the smallest and the largest, you can just pack the largest always. Right? So if you want to pack two-dimensional disks of dimension between 1 and 2, of radius between 1 and 2, just pack disks of radius 2, because anyway we are getting this kind of ugly approximation, so it doesn't really matter. But if you would really have disks that are very different sizes, I wouldn't know how to approach it either. And that's about it for my presentation. Thanks for your time.